Welcome to another data science deep dive on our technical track. In the following presentation, we have two presenters, Christina Echagarruga and Sarah Koehler, both data scientists at Scribd. Obtaining spurious results and hypothesis tests is a significant risk for data analysts and business users when tools and methods are easily or accidentally or intentionally misused. Christina and Sarah cover two scenarios where these errors are common: multiple comparisons and sample size estimation. They will discuss the pitfalls in the currently available tool sets and how they affect your results and how also you can build solutions to help avoid them. Enjoy the presentation.
Hi everyone, I'm Chris and I'm presenting with Sarah. We're both data scientists at Scribd and we're excited to present two methods that we implement to avoid spurious analyses during experimentation with automation. So first we wanted to start out with our backgrounds because we know that everyone comes into data science with different experiences. I recently defended my PhD in biomedical engineering, where I studied blood flow in the brain. While in grad school, I started to explore data science and decided that I would really enjoy working within this data science space. After completing my PhD, I was an Insight Data Science Fellow. And then in November of last year, I started to work for Scribd, which is an ebook and audiobook subscription service.
Hey, I'm Sarah and I work with Chris at Scribd as a data scientist as well. My academic background is in anthropology and with a master's in statistics. I've had a pretty winding path to data science, and some of my past gigs have included being a high school math teacher here in San Francisco. I did epidemiology research as a graduate student and published an R package. I was a Fulbright scholar to Sri Lanka studying classical dance. And yeah, I've had a number of other gigs, and it follows that I really enjoy the variety of work in data science, especially at Scribd. We get to perform a lot of different kinds of tasks, from data engineering to statistical analysis to machine learning and everything in between. Next slide. So yeah, like Chris said, we're going to talk to you guys about a couple of different ways that we're combating common errors in the process of experimentation. So it's easy to get spurious results by accidentally or sometimes intentionally misusing analytical tools. And a couple of the examples that we're going to talk about are, it's easy to find false positives when you're doing multiple comparisons and using comparing different variants or metrics without adjusting the significance level. And also, online sample size calculators often make a lot of assumptions about what your specific test scenario is that may or may not be true. And so we're going to talk about some of the pitfalls with online sample size calculators and how we solve that at Scribd. So yeah, I'm going to start by talking about multiple comparisons and a specific scenario that I encountered. So my motivation for working on this particular project involving multiple comparisons here at Scribd was that after we identify a winner or like a winning variant from an A/B test, we wanted to learn more about the differences in the rate or the mean between the test and control variance for different segments of our population. So this is not necessarily to make a decision about which variant to release, but more to just learn about how our changes affect different segments of our population. So for example, did the winning variant work better for every country? Did it work better for every language, platform, etc.? So this will help us learn more and inform future experiments. So the hypotheses that I landed on to address this problem were the following. So the null is that the country's variant rate is the same as the rate from the control group, as opposed to the alternative where the rates are different from each other. So I'm just using country as an example of a explanatory variable that you might be interested in, but it could be, again, anything. So there's a visualization of this problem on the right-hand side. I've got at least a subset of the countries listed out. But in reality, we want to test all 200 or so. And then there's a difference in the rate for each one of them. And we want to know which of those differences are statistically significant and which are just due to noise. All right, so since we want to understand the differences in the metric of interest, whether it's a proportion or mean, for individual levels of the factor or segments of the dimension, whatever you're used to referring to that as, I knew I was going to need to use Z or T tests with multiple comparisons. And the multiple comparisons comes in because I'm taking a difference of rate for every country instead of just one. So there are a lot of multiple comparisons procedures. Here is just a subset of them. Some of these methods can be applied to the situation that I'm talking about, and some are for slightly different situations. So typically at Scribd, we had been using Bonferroni for every case of multiple comparisons that we did. But Bonferroni is not always the best choice, although it is a really simple procedure. So it's not always the best choice because it can be really conservative, meaning that you're not going to find many false positives at all. But the power for using Bonferroni is going to be really low. So having low power means it's going to be difficult to detect any effects that are really happening. So after some consideration of some of these other methods that apply to my situation, I chose to use Benjamini-Hochberg, the last one on the list, because it's a lot more powerful when you're making a lot of comparisons. And I'm going to talk about some of the differences between Bonferroni and Benjamini-Hochberg and show how Benjamini-Hochberg works. Next slide. So I want to start with the scenario of making no adjustment for multiple comparisons. So normally when we do an A/B test, a lot of people set alpha, the significance level, at 0.05. And what you're doing when you set that is you're saying that you're setting a rate of the probability that you find a false positive in that test is 5%. So when you're setting alpha and using the Bonferroni method, you're actually setting a different kind of error rate, and that's called the Familywise error rate. So to understand this rate, I need to tell you what a family is here. So a family of tests just means a group of tests or comparisons that you're making. So in my example earlier, it would just be the 200. I'm doing a comparison for each of the 200 countries, and that's one test family. So test family is actually kind of an arbitrary thing that the statistician has to decide on themselves. But in any case, the family-wise error rate that you're setting when you set alpha for the Bonferroni method is defined by the number of test families that have at least one false positive out of the total number of test families. So here's an illustration of this. There are 20 test families here, and if we have alpha equal to 0.05, it's really, really small, but you can see up in the top left corner, there's one little dot outside of the circle representing one test family that has one false positive. So this is a really conservative method. Almost no families here have any false positives at all. So by contrast, the Benjamini-Hochberg procedure allows for having more false positives than Bonferroni. So what you're setting with Benjamini-Hochberg is actually called the false discovery rate, as opposed to the family-wise error rate with Bonferroni. The false discovery rate is defined by the number of false positives in a single test family out of the number of significant tests or significant results that you found in that family. So here's an illustration of that. You can see there are a number of false positives for every test family here because there was a non-zero false discovery rate that whoever set. And so yeah, this might look worse, but the trade-off is with power. So Benjamini-Hochberg has much, much higher power than Bonferroni when you're making a lot of comparisons. And each one of these little dots, I think, is a comparison. So in this situation, we'd want to use Benjamini-Hochberg. Okay, so here's how the Benjamini-Hochberg procedure actually works. It's slightly more complicated than Bonferroni, but not a lot. So once you have p-values for each of the t-tests or z-tests that you performed, so each of your comparisons, you're going to order and rank the p-values from smallest to largest. So you can see this example. And then you're going to compare each of the p-values to a cutoff. So how you get the cutoff is you take the false discovery rate that you've set and you divide it by the number of comparisons that you're making. So in this example, the false discovery rate was set at 0.1, and we'll pretend there were 10 tests. There aren't 10 here, but pretend there are. So if you divide 0.1 by 10, you get 0.01, and you can see these cutoffs that step up by 0.01 from 0. So to identify the significant effects, you find the last p-value in your list that is still smaller than its cutoff. So here you can see the last blue line, children, has a p-value of 0.042, which is smaller than 0.05. And then anything above that last line is actually considered significant, even if the p-values are larger than the cutoff. So here you can actually see that there are a couple of p-values that are larger than their cutoffs. But we still consider everything above that last line to be significant. So everything in blue here would be considered a significant effect. So to illustrate this a little bit more, I ran a simulation for a family of 100 tests, and I ran it multiple times to get these results. So with Bonferroni, my family of 100 tests, I had an average power of 0.1. Whereas my average power using Benjamini-Hochberg was 0.66, so that's quite a drastic increase in power. And again, Bonferroni is going to be really strict on false positives, and you'll see hardly any. Whereas with Benjamini-Hochberg, you're going to allow the probability of having some false positives in each test family, but the trade-off in power is really large if you're not so concerned about the cost of a false positive. So if false positives are relatively inexpensive, I guess, for you to find, and you're more interested in detecting effects that really are there, Benjamini-Hochberg is a good choice. Next slide. So yeah, to sum up all of that, if you're in a multiple comparisons testing situation, so maybe your situation is like mine and you want to compare rates for different levels of a factor, or maybe you're comparing a whole lot of test variants against each other or a lot of metrics, then you're in a multiple comparison situation, and it's good to use Benjamini-Hochberg when you want to perform a lot of comparisons, so more than just 2 or 3. And you want higher power than you get with Bonferroni, but you want fewer type 1 errors than with using no correction at all. Benjamini-Hochberg works best for you when false positives are not costly, and you're more interested, again, in finding effects that are really there. And actually, with either of these methods, you want to have independent tests, with a few exceptions for Benjamini-Hochberg that are beyond the scope of this talk. So to make performing the Benjamini-Hochberg procedure easier at Scribd, I created an internal Python function to perform the procedure in 1 line of code. And you can see it right here. Different programming languages do have a built-in Benjamini-Hochberg procedure, but I wanted to sort of customize the inputs and outputs according to what my team is used to using. And so I made my own, and it wasn't too difficult because, as I showed you earlier, it's just a matter of ordering and doing some division. So it's a pretty straightforward solution to implement in a lot of situations. And now I'll hand it off to Chris to talk about some of the pitfalls with automatic sample size and how we solve them at Scribd.
So the second way that we combat false results during experimentation is in how we determine sample size. As you can imagine, we want to make sure that we get the correct sample size. So if the sample size is too small, the results that we get could be skewed. We're also not getting a good picture of what the population looks like. And we also oftentimes won't have enough power in our results. On the other hand, if the sample size is too large, the experiment becomes more complex and also more expensive because we have to spend time without implementing potential changes onto our website. So there are sample size calculators that are available online. This is an example, a very simple example from SurveyMonkey. And as you can see, you just put in 3 different metrics here, and it outputs a sample size. The issue is that our team has spent a lot of time trying to find an online calculator that's accurate, and it becomes more complicated when you have experiments, for example, with looking at multiple comparisons. And many of the calculators that are available online aren't accurate for these situations. And also, what exactly goes into the calculations isn't entirely accessible for understanding for the users that might be coming to it, or for business users like product managers. So what affects sample size? Many of these metrics are probably familiar to you guys, and they are what go into online sample size calculators. For example, the number or the statistical power in your experiment, the effect size, but also going into sample size should be the number of variants and the test split. The issue, as I mentioned before, with a lot of online sample size calculators is that it's unclear how they take into account all these factors. So one thing that has been important for experimentation at Scribd is the test split. And this is the split between how many samples will go into the control group versus the variant group. So if you look at this graph on the x-axis, you have the samples, or the percent of samples that will go into the control group. And what you can see is that as you decrease the number of samples that go into the variant group, therefore increasing the number that go into the control group, you see that the number of samples that are required for your test increases by a lot. For example, if you have a 97-3 split, meaning that 97 of the samples go into the control group, that requires 9 times the amount of samples as a 50-50 split. But if you go down to a 90-10 split, the sample size change is more manageable. So the details like this are one factor that's not included in online sample size calculators. The effect size is another factor that's not clearly calculated in many online sample size calculators. This slide is just to show you that on the left, this is the effect size for comparing means, and on the right, it's the effect size for comparing proportions in the 2 different groups. And each of these produces a standardized effect size so that different numbers that are in different, that have different weights can be compared to each other. And so for online sample size calculators, this isn't, it's not entirely clear how this is implemented in them. So given all of these pitfalls for online sample size calculators at Scribd, we built a custom sample size calculator. And these calculations can be done pre-test and post-test. So pre-launching one of our experiments, we can put different metrics into this calculator and then calculate the sample size that we want. And we can also test out different values for how many samples will go into each variant, and then calculate the sample size and get a ballpark estimate. And then also we can, post-launching of one of our experiments, we can, after 3 or 5 days of the experiment running, we can check the calculator and get a more accurate sample size based on observed data.
Yeah, so to sum up what we've talked about here, we want you to have these takeaways. So first of all, perhaps consider Benjamini-Hochberg as a multiple comparisons testing procedure for when you're in any situation where you're making multiple comparisons, doing multiple z-tests or t-tests at the same time, so that you have a more controlled understanding of your error rates. And we'd also like you to be wary of online sample size calculators, because it can be difficult to know what inputs they're accepting, what assumptions they're making, and the underlying code for those calculators isn't always accessible. And then some further work that we are considering doing down the line is adding functionality to our calculator for means, since those have the added complication of having to estimate a standard error to put into the calculator. They're just slightly more complicated. And then we're also considering open sourcing that sample size calculator that Chris showed for the public to use. So thanks for your attention, and we can use the rest of the time for questions or discussion.
That was a presentation by Christina Echagarruga and Sarah Koehler, data scientists at Scribd, where they discuss hypothesis tests and where these errors are commonly found. They also talked about pitfalls and currently available tools and how they affect results and how to build solutions to avoid these pitfalls. If you'd like to watch more videos like this one, you can subscribe to the DSS Insider program, where you can see our complete on-demand video repository from a wide range of similar topics. Subscribe in the link in the comment section, and also follow us by clicking below. Thank you.